morning everyone. Today in this lecture on mechatronics, we are going to discuss the acceleration and vibration measurement sensors. An accelerometer is a sensor which is designed to measure acceleration or rate of change of speed due to motion, vibration and impact events. And these accelerometers which measure acceleration are normally mechanically attached or bonded to an object or structure for which the acceleration has to be measured. Now, these accelerometer detects acceleration along one axis and they are insensitive to motion in orthogonal direction, okay. And strain gauges or piezoelectric element constitute the sensing element of an accelerometer which sense basically, okay, the acceleration, and how they sense the acceleration that we will be discussing during next 30 minutes, okay. And these devices that is piezoelectric elements or strain gauges, they convert acceleration into the voltage signal and these voltage signals are basically sensed. Now, the design of accelerometer is something like this. So, you have the vibrating object over here whose acceleration is to be measured, and there is a seismic mass basically, and this seismic mass is attached to the vibrating object with the help of a spring and damper, as you can see here, and there is a displacement transducer which constitute the measuring device, okay. And these all elements are placed inside a housing, what we call it as the accelerometer housing, okay. And in this one the basic principle is that as the object accelerates, there is relative motion between this seismic mass and the vibrating object, okay. So, here I am representing by xi the vibrating object motion, that is I am using subscript I to indicate that it is input, and xo I am indicating say the displacement of the seismic mass, which actually indicates the output, okay. So, rather output is relative displacement between the seismic mass and the vibrating object, okay. So, a displacement transducer can be used to sense the relative motion between the seismic mass and the vibrating object, and as we will be seeing, okay, the measure of this relative displacement is basically the measure of the acceleration, and this we could achieve with the help of the frequency response analysis, and from there we can find out that the displacement transducer output to either the position or the acceleration of the object, okay. So, one can relate from frequency response analysis the displacement transducer output to either the absolute position or the acceleration of the object. To perform the frequency response analysis of the accelerometer, let us draw the free body diagram of the seismic mass m here, okay. So, I am representing the relative displacement between the seismic mass and the object as xr, that is here, this is xo and xi. So, the relative displacement is represented by xr here, that is xo minus xi. Okay. And so, this is when I am considering x, so in this direction. Okay. So, if the direction of motion is in this direction, the spring force will be kxr here, and the damper force will be cxr dot. Okay. Now, so this is the free body diagram. I can write the equation of motion for this system as what are the unbalanced forces here, that is minus kxr minus cxr dot, and these are opposite in direction of motion xo. So, I am putting a minus sign here, and these are responsible for the inertial force. So, I am putting it m x 0 double dot. Okay. So, this is how I am doing. Now, from here I can substitute for x 0 double dot as xr double dot plus xi double dot. Okay. So, from here I can get x 0 double dot is equal to xr double dot plus xi double dot. So, I am substituting it here. Okay. So, this is minus k xr minus c xr dot, and I can take all the xr's left hand side, and xi is out right hand side. Okay. So, this is what I get, m xr double dot plus c xr dot here plus kxr is equal to minus mxi. So, here you can see that right hand side I have got the input and expression related with input, and left hand side I have got the expression related with the relative displacement of the seismic mass. Okay. That is the displacement between the seismic mass and the body whose acceleration we are trying to measure. Okay. So, this equation is a second order differential equation which measures, as I said, the relative displacement xr or rather which relates the relative displacement xr to the input displacement xi. So, we had this expression mxr double dot plus cxr dot plus kxr is equal to minus mxi double dot. Now, let us divide by m. So, here what I get c by m here and k by m here, and here we have only this one. Now, let us define these two terms, omega n square is equal to k by m and zeta square as c square by 4 m k. Okay. So, I am defining the two terms like this. Okay. So, from here zeta is actually what c by 2 under root m k. Okay. And now, let us substitute these values in this equation. So, what we get here is xr double dot plus c by m basically. So, you see my zeta is c by 2 under root m k. So, what is my c by m? So, zeta by m, I am dividing both sides by m, and I am taking this to that side. So, this is 2 under root m k. So, this is my c by m. Okay. So, this is zeta 2 and under root k by m. So, this is basically your c by m. So, what is this? This is 2 zeta and omega n, and this is c by m. So, I am substituting it here 2 zeta omega n here in place of this c by m. So, this into xr derivative plus this is my omega n square xr is equal to minus xi. So, this is how I get the equation of motion for the seismic mass, which is written in terms of the relative displacement as the output between the relative displacement of the seismic mass with respect to the object, and xi is the input. Now, for a frequency response analysis, we can assume a certain input, okay, input displacement. So, let me have x t I t is equal to xi sin omega t, and this is of sinusoidal form, and this has got a frequency omega, and the say the amplitude is xi. Okay. Now, since the system is linear, the resulting output displacement will be given as XR is equal to XRT is equal to XR sin omega t plus phi. Okay. Since system is linear, so output will be also going to be of same frequency, but different phase different phase. Okay. So, I am using here the same frequency omega as I am using over here, and I am taking a phase say phi. Okay. So, this is how I am assuming my relative displacement to be. Now, let us take a look at the equation again. So, this is the equation which we derived in the last sheet. If I take the Laplace of both the sides, then what we get over here is basically this will be s square x r, okay, plus 2 zeta omega n s x r plus omega n square x r and is equal to minus s square x I. Okay. So, this is what I am going to have. So, from here I can take x r out. So, I have s square plus zeta omega n s plus omega n square is equal to minus s square x I. Okay. So, from here I can get x r upon x I as s square divided by minus s square divided by s square plus 2 zeta omega n s plus omega n square. Okay. Now, what we do is that we replace this s by j omega. Okay. So, I can do that. So, x r by x I is this is j omega. So, s square will be j square omega square. So, I have omega square and j square will be minus 1, that minus and this minus gets cancelled. So, I have positive thing. This s square will be minus j square omega is j square omega square, and that j square is minus. So, we have minus omega square here plus 2 zeta omega n and s is j omega plus omega n square. So, this is how I get from this to this equation. Now, let us divide the numerator and denominator by omega n square. So, what we have here is x r upon x I is omega by omega n square divided by here we are going to have 1 minus here omega square by omega n square. So, this is what I get plus here I am dividing by omega n square. So, I will be having 2 zeta j omega 2 zeta j omega by omega n. So, I reach to this equation. Now, what I can do is that I can simplify this thing, I can simplify this thing. So, what I do is that I take this omega this side. So, I have x I omega square, I take this omega n square this side. So, I have it is here, and in the right hand side I multiply with a complex conjugate here, okay, that is the same term with a minus sign over here, okay, and I simplify. So, this is the complex conjugate, and when term, and when that term is multiplied with this one, this is what I get. Okay. So, this j square will be yes j square minus will be minus plus and contribution from other term will make it positive. So, this is positive and this is what I am going to get. Okay. So, this one I can write the real and imaginary portion separately over here. Okay. So, as you can see that this portion is my real part and this portion is my imaginary part. Okay. So, from this one I can find out the amplitude ratio and phase angle. Okay. So, amplitude and amplitude ratio I can find out say this is if this is your x and say this is your y. So, what will be the amplitude ratio? Amplitude will be actually x square plus y square. Okay. So, that we can find out. So, if we do that from that expression, this ratio is going to be this one, and the phase will be basically tan inverse of y by x. So, this is what I am going to get. Now, let us look at these expressions. Okay. So, let us look at these expressions. Fine. So, first let us look at this expression here. So, xr omega n square by xi omega square is going to be 1 by 1 minus omega by omega n square whole square plus 2 zeta omega by omega n whole square. I give this some name h a omega. Now, to relate the relative output displacement signal xr to the input signal input acceleration, that is xi double dot, this is what I have been talking to you since beginning. So, this is what I assume my input signal to be xi sin omega t. So, xi double dot will be minus omega square xi sin omega t. Okay. So, here we can see that the amplitude of the input acceleration is basically omega square xi. Okay. So, omega square xi is the amplitude of the input acceleration, as you can see, and where is that term? That term is over here. Okay. That is omega square xi I have over here. So, next let us see if I plot this h a, this term which I have written over here. Okay. If I plot this h a with omega by omega n, this is what the plot is going to be. Now, here I want to mention one thing, that at the damping ratio 0.707, okay, you will see that most of this part is straight basically, okay, until unless it reaches a omega by omega n value of 1. So, one observation is that most of this part is straight, and the other observation is that this for this to have a straight line portion, to have this omega by omega n value should be small. Okay. Rather omega n and this omega by omega n can be small if your omega n is large. I will be coming back to this point little later. Okay. And if I plot the phase response of an ideal accelerometer, then you can see that this value, that is around 0.707, we get almost a linear type of curve. So, if what I was talking to you here about this range, okay, where we have the h a omega as 1 at zeta is equal to 0.707. So, what I was saying is, if we design the accelerometer so that this h a omega is almost equal to 1 over a large frequency range, then I can write from this equation, equation, okay, xr omega n square is equal to xi omega square, because this value is going to be 1. Okay. So, I write xi omega square is equal to xr omega n square divided by h a omega, and this h a omega, as I said, this is 1. So, what does this becomes? This becomes xi omega square is equal to xr omega n square, and I have already said that this xi omega square is the acceleration, input acceleration amplitude. Okay. So, this input acceleration amplitude is equal to omega n square times xr, that is the relative displacement amplitude. So, what does this means? This means that if you are able to measure the relative displacement amplitude, you can measure the input acceleration amplitude. Okay. And based on this principle, the accelerometers are made. Okay. So, based on this principle, the accelerometers are made actually. So, here as I was telling you, the seismic mass, and we had the object here, okay, and we tried to measure this value. This is basically gives us the XR value. Okay. So, from where we get this relative displacement amplitude, and so from here if I multiplied this relative displacement amplitude with omega n square, I can get the input acceleration amplitude. Okay. And I have already talked that the largest frequency range resulting in unity amplitude ratio occurs when this zeta is 0.707 and omega n is as large as possible. And why omega n is as large as possible? Because if your omega n is large, your omega by omega n value is going to be smaller, and the more smaller the omega by omega n value here, you can see that the more linear range you will be getting over here. So, that is there. Okay. And also zeta is equal to 0.707 results in the best phase linearity for the system. Now, as I said, we want omega n as large as possible, and how can we make omega n as large as possible? By making this mass as small as possible. Okay. So, if your mass is small, your omega n is going to be large value. Okay. So, because of this accelerometers have got the small seismic mass. Okay. So, thus we can have a small package common to the commercial accelerometers. Okay. And this equation xi omega square is equal to xr omega n square applies to every frequency component lying within the bandwidth of the sensor. Okay. So, if an arbitrary input that is which is coming from the object which is accelerating. Okay. So, if an arbitrary input composed of a number of frequencies that lie within the bandwidth, each frequency contributes to the signal according to this equation. Okay. So, the total acceleration due to the all frequency components is also directly related to the total measured relative displacement. Okay. So, that is there. So, from here we can get in the time domain xi double dot t is equal to omega n square xr t. Next, let us look at another device, vibrometer. Okay. So, in the accelerometer our intention was to measure the acceleration of the object. Okay. In case of vibrometer, our interest is to measure the displacement of the object. Okay. So, we can use the same spring mass damper configuration to measure the displacement of the object. Okay. And we can define say Hd omega is equal to xr by xi. Here I am using the subscript d just to indicate that I am trying to measure the displacement. Okay. So, xi will be from here, xi will be xr by hd omega. Now, here if I do the plotting for hd omega for different values of zeta, you may say that how do we get this hd omega. So, this hd omega will be basically xr by xi which we can get from here. Okay. So, I have the xr by xi from this equation. So, I can get it from here. Okay. So, the xr by xi I can get it from here. So, that xr by xi that is the hd which I get, if I plot that hd for different omega by omega n ratio, then again you can see that here for this damping ratio of 0.707 for this portion, this is a straight line that is almost equal to 1. Okay. So, if we design the vibrometer so that SD is equal to 1 over a large frequency range, then we can see that Xi is equal to XR. Okay. So, that is there, and you can see that this portion we are getting where when the omega by omega n value is high. Okay. And now in order to get the omega by omega n high, you need to have the lower value of omega n. And how do we get the lower value of omega n? Because the lower value of omega 1 we can get if I use the high value of the mass. Okay. That is why these vibrometers have basically a larger mass. Okay. So, the largest frequency range resulting in SD is equal to omega SD omega is equal to 1 occurs when zeta is 0.707 as I said over here, and natural frequency is as small as possible. Okay. So, this is what I discussed in the previous slide, and because we want the smaller value of omega n. So, that we can get by making the mass larger, and that is why the seismographs which measure motion due to earthquake has a larger mass. So, I hope this must have cleared your concept of the accelerometer and the vibrometer. Okay. Now, let us look at the piezoelectric accelerometer. All right. So, in this piezoelectric accelerometer, the system is almost similar. The only thing is the displacement, relative displacement we are going to measure with the help of piezo crystals. Okay. So, I have got the vibrating object over here. Okay. There is a accelerometer housing. Okay. And this is my mass, seismic mass, and what we have is a spring, preloaded spring is there, a damper is there, and here is your piezo crystal. So, this piezo crystal is placed between the mass and the vibrating object, and here you can see that there are two conductive coating which is there here. Okay. So, the highest quality accelerometer use the piezoelectric crystals. Now, when the vibrating object experiences acceleration, we have seen that the relative displacement occurs between the object and the mass due to the inertia of the mass. Now, this resulting strain in the piezoelectric crystal causes a displacement charge between the crystal conductive coating, okay, as a result of the piezoelectric effect. Okay. And this accelerometer requires no external power supply, and it measures acceleration in the mounted direction, okay, that is the along the axis of the spring, and this is the commercially available piezoelectric accelerometer which is there in the market, and one can use it and place it over the object whose acceleration one wants to measure. Now, the piezoelectric crystal is effectively a capacitor, okay, because yes, and a charge source that generates a charge Q across the capacitor plate proportional to deformation of the crystal, and this deformation occurs because of the relative motion between the mass and the object. Okay. So, representing the accelerometer by the Thevenin equivalent circuit, the open circuit voltage V can be given as Q by Cp over here, and this is the equivalent circuit for a piezoelectric crystal where we have the charge source, and this is our Cp. Okay. And typically Q is in the picocoulomb range and Cp in the picofarad range. Okay. So, this is the Thevenin equivalent of the piezoelectric crystal. Now, the sensitivity of the accelerometer is defined as the ratio of the charge output to the acceleration of the housing expressed in picocoulomb per G basically, okay, or this is also expressed as RMS value of the picocoulomb per G or peak the picocoulomb per G, where G is the acceleration due to gravity. Okay. And the output of the accelerometer is attached to a charge amplifier which converts the displacement charge on the crystal to a voltage, and that voltage can be measured. Okay. And these accelerometers are calibrated in millivolt per G for a specific charge amplifier. In general, piezoelectric accelerometers cannot measure constant or slowly changing accelerations, okay, but they are very excellent for the dynamic measurements such as the vibration and the impact. Next, let us see the semiconductor sensor and MEM devices, which are basically the micro electromechanical devices. Okay. So, you see there has been lot of development about producing ICs, okay, and the technique of producing ICs has developed a new class of semiconductor sensor and actuation called the MEM devices or micro electromechanical devices. In 1980, first MEM sensor was developed using this integrated circuit technology to etch silicon and produce a device that responds to acceleration. Okay. And it consists of tiny silicon cantilever with integrated semiconductor strain gauge. I hope all of you must be knowing the cantilever. Okay. So, we have a small device, it consists of tiny silicon cantilever with integrated semiconductor strain gauges. Okay. So, here could be a strain gauge and this is your cantilever. Now, what happens? Acceleration deflects this cantilever due to inertia and the strain gauge sense the magnitude of the acceleration. MEM accelerometers are now used at variety of places. Okay. So, they are used in automobile to control the airbag system, and also they are used as a pressure sensor for your automobile tire pressure monitoring system, that is TPMS devices, and MEM sensors also include accelerometers and gyros for detecting orientation and motion of video game and TV controllers and other portable electronic devices such as smartphones and cameras. Now, ICs are made basically by a series of processes, and these processes consist of photoresist lithographic layering, light exposure followed by controlled chemical etching followed by vapor deposition and the doping. The chemical etching process is important because tiny mechanical devices can be created by a technique known as micro machining, okay, and usually using carefully designed mask and time immersion in chemical bath, micro miniature version of accelerometers, static electric motors and hydraulic or gas driven motors can be formed. Semiconductor sensors design are based on different electromagnetic properties of doped silicon and gallium arsenide and a variety of ways that they function in different physical environment. The piezoresistive characteristic of doped silicon. The coupling between resistance change and the deformation is the basis for semiconductor strain gauges and the pressure sensors. The piezoresistive effect describes the change in the electrical resistance of a material due to applied mechanical stresses. Okay. So, you know that the piezoresistive effect is different from the piezoelectric effect. Okay. Now, in contrast to the piezoelectric effect, okay, the piezoresistive effect only causes change in resistance, okay, and it does not produce an electrical potential which is there produced in case of the piezoelectric effect. The magnetic characteristic of doped silicon, principally the Hall effect, which I have discussed during my previous lectures, okay, are the basis of semiconductor magnetic transistors, where the collector current can be modulated by an external magnetic field. Electromagnetic waves and nuclear radiation induce electrical effects in semiconductor, forming the basis of the light color sensor and other radiation detectors. The thermal properties of semiconductors are the basis of sensors such as thermistors, thermal conductivity sensors, humidity sensors, as well as the temperature sensors ICs. Now, let us look at the SAW, that is the surface acoustic wave. Okay. So, these are important class of MEMS sensors basically, okay, and it consists of the flat piezoelectric substrate with metallic pattern lithographically deposited on the surface. Okay. These pattern form the interdigital transducers and reflection coupling grating. So, this is the interdigital transducer and this is the reflector grating, and there is an antenna. Okay. So, that is there, and these antennas receive and transmit the signals, okay, and we will be seeing the use of the SAW in these type of sensors. So, an integrated an interdigital transducer, that is IDT, or is a device which consists of two interlocking comb shaped metallic coating. Basically, you can see here this is the interlocking comb shaped metallic coating, okay, in the fashion of zipper, which are applied to a piezoelectric substrate, okay, such as the quartz or lithium niobate. Okay. So, that is there. IDTs are primarily used to convert the microwave to the SAW, that is the surface acoustic wave. Now, an input signal applied to an interdigital transducer excites a deformation in the piezoelectric substrate grating and an acoustic wave that propagates on the surface. Okay. And conversely, a SAW can induce voltage in the interdigital transducer, resulting in an output signal. Okay. Now, let us see the application of this. Okay. Its application can be found in actually wireless identification systems of say car. Okay. So, the device is used in the automatic highway toll plaza to identify the vehicle. Okay. So, how this process work, how this system works basically. So, the micro measurement system has sensors. Naturally sensors will have along with that the signal processing circuit together with hybrid circuit that has the transducer, analog to digital converter, programmable memory and the microprocessor. Now, a transmitter sends out a pulse that is received by the passive SAW device via the antenna. Okay. Now, the resulting SAW wave is reflected as a pattern of pulses unique to the spacing within the reflector grating. Okay. So, here this is the reflector grating. So, the reflected signal pattern will be depending on how this reflector grating is formed. Okay. So, that is how that is there. Okay. So, the pulses are retransmitted through the same antenna back to the receiver along the identification of SAW device. Okay. So, after reflection from this grating, the signal can be transmitted from antenna, and this reflected signal pattern can be there, and with the help of this one, based on this grating, we can identify the vehicle. So, this is the use of this technology. Now, there could be further applications. So, silicon micromachining technique has developed helped in the development of many microsensors. Basically, vision microsensor have found application in the medical technology. Fiber scope of approximately say 0.2 mm in diameter has been developed to inspect flaws inside tubes. Okay. See the dimension size 0.2 mm. Okay, is there a micro tactile sensor which uses laser light to detect the contact between the catheter and the inner wall of the blood vessels during insertion, has sensitivity in the range of 1 millinewton. Okay. So, if this much 1 millinewton force is there, then even this much force can be detected. Okay. Similarly, the progress in the area of nanotechnology had led to the development of nanosensors, and this help in miniaturization and are expected to open the new avenues for the sensing applications. So, this is the reference Alciator and Histon, Introduction to Mechatronics by McGraw-Hill, published in 2014. This book has got very good material, whatever I have discussed in that. So, you can refer this book for the further reading and doing the exercise problems. Thank you.